Welcome to the lecture series on deep learning in artificial neural networks. This video covers RMSprop and ADAM, two widely used methods for gradient descent in the context of mini-batch updates. Let us consider downward movement on an error function that may contain a saddle. Instead of this three-dimensional configuration, I like the two-dimensional plots with contour plots of the error function, also called loss function. And suppose that at the beginning we move to a first location here, and now we have to evaluate the gradient. The gradient goes down on this error surface, which contains two minima, a minimum here, another minimum there. And now we just calculate the gradient, and this is where we go. And then we get close to the saddle, we slow down, and slowly we will turn around before we go to the minimum. So this is the situation that you have in the context of batch gradient descent. However, if we do mini batches, then each mini batch sees a different data set, a different sample of the data set. And therefore, each mini batch sees a slightly different error function. The error function for a small mini batch is not identical to that of the true full batch. So at this very same location, in one mini batch, the gradient signal might go in this direction, and for this mini batch, it might go in this direction. For the third one, it goes down here. So it's always the same starting point, but what the gradient descent algorithm sees is a different error function because it sees different data. Therefore, for one mini batch, it would see this minimum. For the other mini batch, it would see the other minimum. And this is even more extreme if we work with stochastic gradient descent, where we have only one data sample at a time. So here is stochastic gradient. We have one sample at a time, and we start here. The true error function would give a gradient in this here, but since the data is noisy, since we look at one sample at a time, for one sample it looks this way, for the next one this way, for the third one this way, for the fourth one this way. So now the aim is to estimate the true downward movement from the mean, and to get a feeling of the quality of our estimation, we may also want to estimate the variance from a finite number of samples, for example from k samples. Now instead of the variance, we can also just estimate the second moment, which is a squared gradient, but without subtracting the mean. So before we discuss the algorithms RMSprop and ADAM, let's just think together, what would we want? What would be a good optimization algorithm? Well, should a good optimization algorithm have different effective learning rates for each weight? Well, that's what we have seen with momentum. Is that something desirable? Should it have smaller update steps for noisy gradients? The gradient is noisy if we do mini batches. The gradient is noisy if we do stochastic gradient descent. If so, why? Then should the weight change be smaller for small gradients than for large ones? Let me explain this. If I do a one-dimensional plot of the error function as a function of the weights, then if I go here, I have a big gradient, so the effective update step is bigger than if I'm down here, because now the gradient is smaller, so the step size is also a bit smaller. Is that what we want? Or should it be the other way around? The weight update should be larger for small gradients, or the weight change, so this actual size of the weight change, should it be always the same? Of course, not at the minimum, but otherwise. So what do you think would be good? And then these algorithms, RMSprop and Adam, will make certain choices. So here are the basic ideas of the two algorithms, RMSprop and Adam. We always have a weight change that we calculate by a gradient. In the real gradient, it would be the sum over all samples, but we look at stochastic gradient, so we have one sample at a time. This is one specific weight, the weight in layer N from neuron J to neuron I. Now, we want to estimate the mean from K samples, and we can do this, for example, with a running average. We have a first parameter, rho 1, and then this procedure just averages the gradient over roughly K samples. Now, we then do something very similar with the second moment. So we take the same derivative, the derivatives of the same weights, and we square it. So if you think about this, could be a matrix where I multiply different weights, a weight Wij in layer N, a Wkm in layer L, but that's not what I do. This is more like a diagonal element of this matrix. So we just square the individual gradient elements, and then we do again an online average of this squared gradient with a parameter rho 2. Before I discuss the three algorithms in detail, let us consider a very simple example where we have only three weights with simple indices 1, 2, and 3. So then we calculate the updates, and we find that in the first time step, we would have this vector of updates, in the second time step this one here, and in the fourth time step this one here. Maybe it's more interesting to follow this as a function of time, and then we see 1.1, 0.9, 1.1, 0.9. Well, if we calculate the average over K samples, then this average for the first weight would be just 1. Let's do the same for the second weight. This one is easy. Delta W2 is 0.1. Let's do the same for the third weight, 1.1 minus 0.9. Let's calculate the average, and this is also 0.1. Now let's look at the squared gradient. So let's try to do this for the first one. We square it, we take the average, and afterwards I actually take also the square root. So 1.1 squared gives 1.21, 0.9 squared gives 0.81. So if I average over these, I get about 1.01, which for me is essentially 1. Well, doing this for the second weight will be simple. Delta W2 squared average square root, well, this is 0.1. Let's now try to do it for the third weight. Well, you see, once I square this, the signs go away, and so here I will get the same result as for the first weight. Squared average gives 1.01. And now let's be interested in the following. We compare the mean with the square root of the second moment. This squared gradient is called the second moment. The mean is sometimes called the first moment. So the mean over the second moment. Well, this gives what? For the first one, it gives 1.0 divided by 1, so it's about 1. For the second, it's 0.1 divided by 0.1, it's 1. For the third, it's 0.1 divided by 1, so it's 0.1. And now you see, when we think of the questions in the quiz, well, it didn't really matter that the first weight had a mean of 1 and the second of 0.1. Once I divide by the second moment, they come back with the same result. So this scales out the absolute size of the gradient after division with the second moment. Now for the third one, it has the same mean as the second one, but it gets a much smaller update once we consider this as the relevant quantity. And this is because it has the bigger variance. And this is the basic idea of the three algorithms we will discuss in the following, and we start with the RMSprop algorithm. So at the core of these algorithms is this idea that I compare something like the signal, which is the mean, with the variance, but in fact it's not the variance, it's the second moment. The difference is that in the variance I would subtract the mean before I square. And now let's look at these algorithms in their detailed pseudo-algorithm version. So in this notation, parameters are called theta, and the gradient is called g. And this gradient is a mini-batch of size m, averaged over this mini-batch, so I have a 1 over m in front. The gradient with respect to the parameter, and L is the loss function that I often call E for error function. So it's just the mean gradient in this one mini-batch, the average over this mini-batch, the gradient at this mini-batch. And now I do this running average. I accumulate the square of this gradient, and this notation here means pointwise multiplication, and just means we look at the diagonal, gradient index I multiplied with gradient index I. And rho is just this, say, time scale of averaging. So the mean is local, just for one mini-batch, whereas the accumulated squared gradient has this parameter rho that characterizes the spread, the duration of this accumulation period. And then the actual update, and this is what we are interested in, is the gradient divided by this r, divided by this square root of r. And now I have an extra parameter delta, and this is just used to stabilize the division. So if r for some reason would be very small, then this division could explode, and having a fixed delta just stabilizes this. So this is just a numerical trick. And at the end, we just update the parameters with this update step delta theta. So the previous version of RMSprop evaluated the gradient locally for just one mini-batch. Now we add a momentum, so we also have a smoothing over several mini-batches, and we use the Nesterov momentum. The Nesterov momentum means that we evaluate the gradient not at the momentary parameter, but at this interim updated parameter value where we already sort of virtually move forward. The gradient is evaluated again as an average over the mini-batches of size m. the squared gradient is accumulated over some time period that's characterized by the parameter rho. Then we calculate the new version, the new update, the real update, which is the gradient divided by the square root of r, and there should be again a 1 plus delta, this small control parameter, and in the end the whole thing is updated with this value. So the Nesterov momentum comes in by the fact that we always evaluate at this inter-im update location. The Adam algorithm is a variant of these ideas. Again, I have parameters theta, and I calculate the gradient over a mini-batch of size m. The gradient is with respect to the parameters of this loss function L. And now I have a first moment estimate, which has these parameters ρ1. G is just the gradient. I have a second moment estimate with a different smoothing parameter ρ2. G times G is this element-wise multiplication. And then we don't really need this. The real update step is this estimated mean divided by the estimated second moment, square root of the second moment, and again this parameter delta that's used for numerical stabilization. And then this is the final update. So what are those two lines that are jumped? Well, if you do these kind of online averaging, then it takes a couple of time steps until the averaging comes into place. And during these initial time steps, you already work with some slightly corrected version. But this is a detail, is not really important for the functioning of this algorithm. So let's do a first summary and think of our little example with the 3 weights before. In all three, RMSprop with Nesterov momentum and Adam, the parameter movement, the update of the weights, will be slower in uncertain directions. That means directions where there is a lot of jitter. It's faster in directions with less jitter, but the actual size of the gradient doesn't matter if in a noise-free, jitter-free situation, this would be scaled out by this implementation of Adam and RMSprop. So let's finish with the quiz. Let's take RMSprop as an example, or let's take Adam as an example. A good optimization algorithm should have different effective learning rates for different weights. Do you think that this is correct? Yes, this is correct. This is implemented by the RMSprop with Nesterov momentum. This is implemented by Adam, and it's the momentum itself which already gives different update speeds, effective learning rates for each component. Now, in batch mode, a good algorithm should have the same update step, weight update step, delta W, for small grades and for large ones. Batch mode means noise-free. True or not? Yes, this is what RMSprop and Adam do. And the final one, a good optimization algorithm such as Adam should have smaller update steps for noisy gradients if you do this stochastic gradient descent. If you think this is correct, and yes, this is correct, as discussed. So the summary, momentum always suppresses oscillations. It implicitly yields a learning rate that's different for each weight. It's an effective learning rate per weight. And it smoothens the gradient estimate because you average effectively with an exponential filter over several gradient time steps. Adam invariants, in addition to momentum, they adapt learning step size to the certainty of the situation. Weights that have a lot of jitter are updated less than others. It includes momentum, therefore it includes all the features that we discussed above, and it has effectively a small learning step for very noisy directions.